Okay. All right, question number 3 was graphing a trigonometric function. I've graphed a lot of sine for some reason in the past, so I just kind of figured I would do a little tangent one. So just remember, when you're doing tangent, a couple things. You want to make sure you understand what the parent graph is. I'm just going to do the initial period. I'm not going to go crazy. So notice that the shape of the tangent graph, and again, you can identify all of these values by looking at the unit circle, or by using the unit circle, I should say. All right, so this is just going to be one initial period. So between negative pi halves and pi halves, that's going to be 0, and it's going to take on that shape of that nice little S curve. So this is what we call y equals tangent of x, and obviously, again, this graph repeats on and on and on in both directions. So what happens when we take a negative tangent of pi halves minus x? Well, the first thing we need to understand is we want to, if we're going to graph this, we want to understand this as a tangent of bx minus c. Sorry, let's use some parentheses correctly. B times x minus c, double parentheses, plus d. Okay, so first of all, we want the x to be written in front, all right? And if we want a b to be factored out as we can. So what I'm going to do is I'm going to write this as negative tangent of negative x plus pi halves. Now, a lot of people might think that is going to be the final answer, or at least in this format, but it's not. We want to make sure we have that second set of parentheses. So again, this only happens when you have that b, but you want to make sure that you factor out the b. And usually with negatives, that's where a lot of students are going to make their mistakes, is with that negative. Remember, you got to make sure you factor out. Now it's in this format. Okay, so what I'm going to do is I'm going to understand these reflections here first. So it's a couple things. When I have a negative outside of my function, that is going to be a reflection about the x-axis, right? So if you could just kind of take this graph and reflect it about the x-axis, now you're just going to have a nice little curve. Thing. Oh, I did have that. There we go. Let's go get that to red. All right, so when I reflect this about the y-axis here, we're going to have a graph that's going to look, something like that, right? And then I have a negative on the inside of the function. Well, that's going to be a reflection about the y-axis, right? So therefore, if you reflect about the y-axis, then that's going to turn the graph exactly to its original position. And that should make sense to you, hopefully, if you recognize that the tangent function is an odd function. It's symmetrical about the origin, i.e. the x and the y-axis. So the only thing that's really happening now is then we also have this pi halves, this x minus pi halves. So what that's doing is that's just shifting the graph pi halves to the right. So then what I'm going to do is I'm going to take this graph and I'm just going to shift it pi halves to the right. So my graph is now, instead of at 0, that negative pi halves with my asymptote, or my asymptote at pi is now going to be shifted over at 0. I'm now going to have an intercept at pi halves, and if I add pi halves again, I'm going to have a new asymptote. And then the graph is going to take the same shape. Looks really bad like that, but that's okay. So let's just kind of go through the characteristics, because I really don't focus too much on graphing with my students anymore, but I do make sure that they understand how to find the period. Remember, the period for tangent is going to be pi divided by b. So in this case, my b is going to be my coefficient of x, which is 1. So therefore, that's just going to be pi. We also have a vertical, I'm sorry, not a vertical shift. We have a phase shift. And that phase shift is right pi halves. We have a reflection about the x and y axis. And then last but not least, guys, we have to identify where the asymptotes occur. And again, the domain of the function is going to be all real numbers except for where the asymptotes occur. So you can see that the asymptotes here occur at, and this is where kind of the one where we got stuck with a lot of my students. So we can see that the asymptotes of the parent function occur at x equals pi halves, and then the distance they are apart is going to be pi n. And if you look at the unit circle, you could see at pi halves, if you add pi, that's going to take you to 3 pi halves. And that's both going to be undefined values for tangent. However, in this case, I have pi halves minus x is going to be equal to my asymptote. So you can see this is going to be different, right? So when you have a new asymptote equation, or when you have some transformations on the inside, all you're simply going to do is take what's inside of your function and then set that equal to the asymptote equation, which is pi halves plus pi n. Now, again, I can just subtract the pi halves on both sides, and I can divide by -1. Now, dividing by negative, like minus pi halves, pi n, or plus pi n, doesn't really matter. Like, it doesn't matter if you go pi or negative pi, it's still the same direction. So therefore, x is going to equal pi n. So the domain, let's just kind of, domain is going to be all real numbers such that x cannot equal pi n. And let's just do the range as well. The range, you can see that the graph is not bounded, right? It continues indefinitely in the negative as well as in the positive direction.